All right, we're moving on to our next session featuring Neo4j's Dr. Jesús Barrasa. Please don't hesitate to ask questions using the questions tab on your screen. We'll have a brief Q&A session at the end of the presentation and demo. You can also tweet about the session using hashtag Neo4j. Here's Lance Walter to introduce Dr. Barrasa.
Okay, great. For our next session, we're joined by Dr. Jesús Barrasa. He's been with Neo4j for about 5 years in different consulting and industry solutions roles. Dr. Barrasa has a master's degree in software engineering from ENST Paris, as well as a PhD in AI and knowledge representation from Universidad Politécnica de Madrid. Super excited to learn more about using public RDF resources in Neo4j. And with that, welcome, Jesús.
Yeah, thank you, Lance. Yes, I'm Jesús Barrasa. I'm joining you from London today in the UK. And yeah, well, actually, let me say a couple of words about me. I've been with Neo for quite a while, for the last 5 years. But before that, and that's probably relevant for this talk today, I did spend quite a bit of time on the other type of graphs, and that's the RDF graphs. I did my PhD back in 2007 in this particular area. And that's precisely what I'm going to be talking about today. So currently I head the team of sales engineering in EMEA, but I'm probably more relevant again for this talk. And I'm leading the Neo-Semantics project, which is an extension to Neo4j, which is part of our labs incubator, and that precisely is all about integrating with RDF, which is the topic of today's session. So I'm going to try and share how we can leverage the many RDF data sources that are out there, public data sources, especially in the context of life sciences. And yes, that's my plan for today. I would probably say that especially the second half is going to be more useful for people who are already familiar, have a basic understanding of both RDF and Neo4j. But I'll anyway do an introduction and assume no previous knowledge of either of them. So public RDF data sources, what do I mean by that? What do they look like? Well, there's probably a bit of course division, but there's data sets, that's public databases or annotated data sets. But there's also, and that will be on the data side, but there's also plenty of metadata public repositories, and these will be in the form of public vocabularies. If they're a bit more, a bit richer from the semantic point of view, they can be ontologies or even sets of constraints derived from these ontologies. So both data and metadata sources are out there, both published as RDF, because interestingly, and we'll come back to that, RDF makes no difference between data and metadata, and makes it possible to combine and represent the two pretty much in a homogeneous and standard way. So which are the data sources that I'm going to be looking at today? Well, not all of them, of course, but I thought I'd mention it. By no means a complete list. It's just some of the most popular ones. So we'll be looking at the MESH vocabulary, the medical subject headings from the National Library of Medicine. We'll be looking at ontologies published, well, not published, but hosted by the OBO Foundry or the BioPortal, which are repositories of ontologies that include, for example, the gene ontology, the NCBI taxonomy, the disease ontology that you can see also there on the screen. There's many others, for example, the ones curated by the EBI, the European Bioinformatics Institute, like the CanBL or the UniProt with protein information. There's plenty of public information on clinical trials through clinicaltrials.gov. There's probably the most popular, the biggest and growing in importance and in quality, Wikidata, which we're going to be used extensively today. But there's a large set of public resources and that we are going to be accessing, and in a number of ways. Basically, I would say two main ones. So sometimes the whole data set is available for download, and what you can do is take a whole dump of the database and use it locally, or you can access them through APIs, and the APIs can be of different shapes. So we can We can use the Sparkle query language, which is the standard for RDF, and we'll use quite a bit of that today with the different flavors of Sparkle, the construct, describe, or select queries. Or we can use, when it's about linked data, just purely by dereferencing URIs, we can also get RDF. So these are the two main ways. So we can either get a batch approach to the whole data set, or we can just be more selective and do it via query. And we have an example there with the National Library of Medicine, the MESH data download page, where you can see that they offer both access, the download and the link to the Sparkle endpoint. So what's RDF? And like I was saying before, probably 2 words before I go ahead and dive deeper in how RDF can be used in Neo4j. RDF is a W3C standard, and in their own terms is a model for data exchange in the web. It's based on 2 main pillars. So RDF identify things uniquely by using URIs, and that's crucial because we see that at the center of RDF is the notion of data exchange, interoperability. That means that we're going to have distributed data ownership, data coming from multiple different sources that we want to link together nicely, and we're going to use extensively the notion of URIs to identify things in a homogeneous and consistent way. Then the second building block, I would say, is the notion of triple. So RDF is just a set of statements. A statement is a subject, predicate, object triple, as it's called. And by using these 2 building blocks, that's all we're going to need from RDF. I mentioned before that Sparkle is the query language, and we'll see a little bit of it today. And then RDF can be serialized in a number of different formats. Because it's a format for data exchange, you will have many variants of possible serializations. Let me show you a little bit more of that. So I said that RDF represents data, represent any domain as triples, statements. This is a little fragment extracted from the Wikidata, one of the sources that we've been talking about. Like you can see, everything is identified by URIs. And if you look at the first triple, I hope you can see the pointer, my mouse pointer, you see that there's something identified with this long code, Q84263196. That is something that we're providing some statements about. So we say in the first one that the type is a disease. In the second one, we're saying that the label is COVID-19. So that's another statement. And in the third one, we're saying that it's a subclass of another unique identifier, another URI that's described further down. If you see the translation, the visual translation below the graph that they form, is that every single statement, every single triple in an RDF description actually represents an edge in a graph. So you see to the left a ellipse form that represents the first resource, the first URI, and we see that it connects to the type, which is disease to the right. We have a second edge that represents the label, COVID-19, and then the connection to another entity that we see further down that it's another instance of type disease and has its own name, which is a typical pneumonia. So it is a fact that chaining triples form a graph. And we're very familiar with that model because Neo4j uses precisely the graph model to represent the world. I mentioned before that there's multiple ways of serializing RDF data. And just briefly, because we're not going to cover that today, probably worth mentioning that you have a JSON-based serialization, you have an XML-based serialization, you have a more kind of flattened one called ntriples, a more kind of human-friendly one called Turtle. But let's get to the interesting part. It's a graph. So if it's a graph, it should fit nicely into Neo4j because Neo4j uses also the graph model. And well, they're slightly different. There's just 3 basic rules that we're going to use to be able to persist RDF data into Neo4j. So we've seen that the triples in a statement can be of basically 2 different types. And if we classify them by looking at the object, the third element in the triple. So it can be a literal, and the literal is something like the COVID-19 that we saw before. I hope it's readable in this slide. And if it's a literal, then it will become in Neo4j a property of a node. The essential difference between RDF and Neo4j is that nodes in a property graph, like the one Neo4j implements, have internal structure. They can have properties. They can have attributes. So every triple that has as value over the object a literal, we're going to store it as a property of a node. When the object of the triple is another resource, essentially what we're describing is an edge, and that will translate into a relationship in the property graph. And finally, if there is a type statement, so it's a classification statement in RDF, we're going to use, probably, it's an option, the notion of labels in the property graph. Labels, as you know, in Neo4j are tags that we can associate to nodes in order to classify them, to build categories of nodes. So these three simple rules is something that, of course, you're not going to be need to take care of, because the Neo-semantics library will do it for you. So, as I mentioned before, Neo-semantics, or N10S for short, is an extension of Neo4j that will simplify the integration with all sorts of RDF resources. Today, we'll be focusing on importing data into Neo4j, but it can also be used for other things like defining mappings, exporting, doing some basic inferencing, validation. But for what will be focused the session today, the important thing is that it will apply these input rules and make it really, really simple to get RDF data into Neo4j. And once you have it in Neo4j, you can integrate with data from other sources, you can query it using Cypher, and do many more things, as we're going to see. Good. So again, very briefly, we get the data, and we're going to be focusing on the more API-based access to public data sources. And hopefully everything goes well. I'm going to show how to run some queries on these public data sources. So we can run different types of Sparkle queries. One of them is what's called a select query. And these produce a set of variable bindings, a table structure. Well, if your Sparkle query returns a table structure, then we don't need to deal with RDF. What you have is a table that you will import into Neo4j pretty much in the traditional way, I would say, using load CSV or using APOC or any other methods there. Now, if your API or your Sparkle query returns triples, returns RDF, then you want to be using Neo4j N10S or Neo-semantics, because that will basically implement the logic that we just described. Good. So that's what I'm planning to do today. So I say 20 minutes. It's probably going to take a bit longer. But the idea is, and I refer to this article, this research document by Gardner, sorry, that was published just a couple of weeks ago, where they talk about the relevance of and the importance of building knowledge graph to drive AI enterprise applications. But they introduce a very interesting topic, which is this notion of a minimum viable graph, MVJ, minimum viable knowledge graph, if you want. And it's this idea of building things incrementally, building things in an agile fashion. So we don't want to boil the ocean, which is something that happens pretty much in every semantics-oriented project. So we want to be focusing on a particular use case, and then we'll take it from there. I mean, we'll keep extending the graph, which is something that's natural to graph projects, because they're built to be extended naturally as new data sources or as the domain expands over time. So let's build this minimum viable graph. And what are the sources that I'm going to be using for these? Well, there's 4 main ones depending on time. So the first one is Wikidata. Wikidata is, like I was saying, one of the most popular ones. And I'm going to be extracting from Wikidata information on viruses, taxonomy of viruses, but also infectious diseases. And probably as well some chemical compounds information. I'll get the same information also from the MESH, the medical subject headings from the National Library of Medicine. And I will try to put them side by side and compare them and run some interesting analysis on them. I will complement the whole picture with information from the disease ontology. And if we have time, maybe bring some scientific literature from the Microsoft academic graph. The idea is to build a graph in Neo4j where I can do my local analysis. So that's the objective. And well, let me actually jump into the demo. So I'm going to start sharing my screen. I hope it's visible to you. So what you see in front of you now, it's the Neo4j browser. This is a browser that's pointing at my local Neo4j instance. And what I'm going to do, literally start from scratch, is I'm going to create a new database. I'm going to call it Connections Life Sciences, right? So if I create my database, I'm going to say I'm going to use that database. There we go. So we have an empty database, and I'm going to interact with the database to do all the input, all the RDF input, partially directly here in the browser. But I'm also going to use a graph app that we have. It's called Neo Semantics, and that will do a lot of this transformation of RDF into Neo4j in a much more user-friendly way. So I'm going to ask it to use the local graph. I'm going to pick up the CLS, which is the one I've just created. And the first thing the app is telling me is that we're going to have to create a constraint. I just accept, and it will create a constraint for me. That's basically to index all the resources that we're going to be bringing by URI. URI is the unique identifier, as we discussed before. Good. So first thing before we start is create a configuration. And without going into the details of what can be done, because there's a manual and I'll refer to it at the end, I'll take all the defaults. And the only option that I'm going to set is that I want to ignore the full URIs in the vocabularies. Why am I going to do that? Well, all the resources that I import are going to be identified by URIs, and that's going to be critical to link the different pieces together. But I'm going to try to make simple the terminology that I use. I'm going to use simple names for the relationships, for the properties, for the labels. And in order to do that, I'm going to use the ignore option so that I don't need to keep all the complete URIs. That might be useful in other scenarios where we might want to maybe regenerate the RDF once it's been imported, but it's not the case in this example. So I'm going to click create the configuration. That's done. And like I mentioned before, everything I do through the app is going to be reflected in my graph. So if I do now config and I show, it's going to list all the properties, including the ignore vocabulary URIs that I've just set. All looking good. Good. So the first data that I want to bring comes from Wikidata. So let me go to Wikidata. I have a handy link here. And Wikidata is one of the public RDF data sources that I was describing before. And obviously, I have to interact with it using Sparkle. I don't think I'm going to have time to explain in a lot of detail every bit of Sparkle that I'm going to be using, but maybe just a high-level overview of what I'm doing here. So this is the API, the Sparkle API that Wikidata offers. And what I'm doing here is I'm writing a Sparkle query that selects from the whole database a taxonomy of viruses. How do I do that? Well, I'm going to use the term 808. Everything in Wikidata is uniquely identified with this numeric codes, right? Q808 represents the notion of a virus, right? So what I'm doing here in my query is I'm looking for anything that hangs off that notion of virus, any category, any taxon, as it's referred to here, that has as parent the notion of virus, so any element. And for every element that matches that, I'm going to get its direct parent, and by bringing pairs of virus parent node, I'm going to be building the whole taxonomy. I'm also bringing the name, the label. And it's worth mentioning that Wikidata is a multilingual database. So I have to be specific here on the language that I want to bring, and I'm selecting English, because otherwise I would be bringing probably all possible translations of the names, and that's probably something I don't want to cover today. So it's pretty simple. That's all the structure that I'm getting, and you can see it in the results down here. So I'm getting viruses, the ID of the parent, the name, and these two optional elements that I have at the bottom is the reference to the mesh ID, and mesh being the medical subject heading, and the reference to the Microsoft academic field of study ID. And that's one of the things that Wikidata is great at, is at cross-referencing data sources. So you have a hierarchy of viruses, but you have links to other data sources. And that's critical to then be able to combine the information together. So that's what my query returns. That would be a select query that, as you can see, it returns a tabular structure. But what I want is a graph. I want an RDF graph. I want a sequence of triples. And that's what I do in my construct part of the query. So what I'm doing there is morphing the result of my, not really morphing because I'm not changing the structure, but I'm renaming things. There's, for example, this 171 that I would like to call something more user-friendly. I'm going to call it has parent because that's what I want imported in my graph rather than this more cryptic 171. Same with 808. I'm going to explicitly call it a virus. Why not? Right? There's one thing that I can or may not include. So if we want to keep provenance information in the Neo4j graph, I might want to annotate things, for example, like I'm doing here. I'm saying, well, this is a node that comes from Wikidata. I can do it, or maybe I can remove it depending on your needs. But that's an optional element. So I'm basically using this section to rename some of the elements and make it more user-friendly. If I rerun the query, that's going to produce a sequence of triples, subject, predicate, object. It's being a bit slow, but hopefully it's still good. Right, and we see that we have now the ID of the virus, its type, which is now looking the way I expect, the name, the parent, the link when it's present to the Microsoft field of study, and the same with the mesh vocabulary. So that's a query that I like. I'm going to copy it from here. Let's copy this, and let's go back to my app. Okay, so one thing that I can do in my app is preview, and that's something that I want to do before I actually run the input itself, before I persist the data into the graph. That's quite useful when I'm kind of in this development mode. So from the app, I can do several things. I can get RDF in a number of ways. I can retrieve a document that's publicly accessible. I can paste a fragment of RDF, literally just inlining it in the app, or I can run a query on a Sparkle endpoint, which is what we're doing right now. So if I select the Sparkle option, what I'll need to do is select the service that I want to query. In this case, it's Wikidata. It's one of the available options, right? It gives us a default query that I'm going to replace with my query. But I guess it's interesting, it's important to know that we have a number of well-known API Sparkle endpoints, but you can write your own. I mean, if you want to query one that's not in the list, all you need to do is type the URL there, and you're good to go. So we can get the data in a number of formats. We're going to use the n triples. There's a number of options that I'm probably going to skip for the sake of to make it more fluid today. But yes, we can run this query. And we can get a preview of what that query returns. And that's going to look very much the same as we got when we run the query through the API. So that returns us a list of triples, as expected, nothing new. But what's interesting is that we can have a graph preview. So we can see what it's going to look like when we import it into Neo4j. And that's the graph as it will be transformed by the Neo-semantics application. There you go. So that's starting to look a bit more like what I want, right? So we see that things are not called 808, but they're called virus. And for the viruses, we get the name and the URI. Of course, the URI, remember, it's critical. And we have the links to the parent, always. And eventually, when present, we will have the link to the mesh descriptor and the link to the Microsoft academic. And the links are called in the way that I've selected. By renaming it in the construct. So all looking good. That's the graph that I want Neo-semantics to build for me. So I'm happy with that. I can actually go back to go now to the import where I'm going to run it for real. So now I'm going to actually remove the limit because I don't want to bring 5, but I want to return everything that the query returns. And yeah, I think we can just click go, and that will import the whole taxonomy of viruses from Wikidata. Pretty straightforward. That should give us a report of the result, and hopefully if the network's looking all right, and it's not, yeah, that's fine. So 35,000 triples imported, all looking good. And we can now go back to our Neo4j database and we should see some virus data already loaded. So let's run a query to see what that looks like. So let's say, for example, that I want to find the SARS virus, SARS coronavirus, and find all the taxonomy of elements all the way to the root to the virus. And the way I do it, well, I look it up by name, severe acute respiratory syndrome coronavirus, and I'm going to follow the has-parent relationship, a variable number of steps, all the way to the root. And I know it's the root because the condition is that the root will have no parent, right? It's the top of the tree. So if I run this, we should get a structure that, interestingly, and that was unexpected, it's not a straight line because it has some kind of shortcuts, right? So if you see what's happening here, we have at the bottom, of course, we have the SARS virus that we started, and at the top we have the top level category of virus. But we have some kind of strange bits like this one here, where we have a virus connected not only to the parent but also to the grandparent, which is not totally incorrect, but maybe we want to clean it. I mean, I'm not saying that's strictly needed, but I basically mention it because what I want to do is give you tools to see how these sort of sessions typically look, these sessions of importing data from public resources. They won't be perfect. And sometimes, this information might make my graph look a bit messy. So I can run a cipher fragment, and I'll be combining the RDF and the cipher side to remove these shortcuts, right? So I can run this quickly. That will get rid of some of these undesired relationships. And if we rerun the query, now hopefully it looks like a perfect straight line with no shortcuts, and that looks fantastic. Okay, so we've loaded the taxonomy, and we can expand these elements, and maybe some of them will have other child elements, so these viruses will have some others. But interestingly, we have created some, at the moment, empty nodes, which is a link to the Microsoft Academic. At the moment, it only has a URI, as you can see. But hopefully, when we load the data from there, it will magically link together. So we've kind of created the stops to then be able to bring the data and complete the whole picture. And the same with the mesh information, right? Good. So let's do exactly that. Let's go now to the second data source, which is the mesh medical subject headings, which offers pretty much the same type of UI like the Wikidata. So we can run queries there, and I'm not going to go into the details of what I'm doing here with Sparkle, but I'm doing essentially the same thing. There's a top level category in mesh, which is this code that represents the virus, and anything that hangs off that term is going to be part of the hierarchy that I want to import. So you see here that it returns a sequence of triples, pretty much like in the previous case. So I can just grab my query and go back to the app, point at the mesh data source, the mesh endpoint, replace the query, and in this case, I'm going to import it in turtle format. So if I do import, that should bring a few thousand triples, 2,300 in this case. All right. And now we have a virus taxonomy from Wikidata, and next to it, we have a virus taxonomy from the mesh data source. So one thing that we can do is compare the two of them, and that's what I'm going to do in this query. So pretty simple one. This is exactly the one that we used before. So that takes one particular virus. Again, I'm using the SARS one. I'm going to get the taxonomy, and I'm going to do exactly the same on the mesh side. And the way to get from the Wikidata one to the mesh one is following the same as mesh descriptor that I just created. So if I run this query, that's going to hopefully show me the two hierarchies. So we have it's going to be a bit tricky to lay it out in a nice way, but we see that at the left, we have the mesh taxonomy, which has broader descriptor, and this one has parent. So we have the two taxonomies side by side, and we have matching elements at different levels. Good. So we have two aligned taxonomies of virus information without much effort, and they're linking together thanks to this the use of URIs. Because I didn't have to really specify how things link together. It's all thanks to the pre-linked RDF data. Good. So we have we've loaded the virus information. Next thing we're going to do is we're going to bring the disease information. And for that, we have another query on Wikidata that, as you can see, will return me information on, I hope I've set a limit. Maybe I haven't. It'll take a while. That's not too bad. Good. So here I'm doing something very similar to what I did before. So I'm going to start from the top level, which is the notion of infectious disease, and I'm going to get all the children of this notion here, this element with its own ID, infectious disease, and I'll follow the subclass of and instance of properties. That will bring a whole tree of infectious diseases connected together. I'm getting this sparkle and passing it directly to my query, which goes directly to Wikidata. Good. Let's set it back to n triples. And if everything goes well, that should bring another bunch of triples, 3,500, representing the infectious diseases from Wikidata. I'm going to do, again, the same, but this time from mesh to be able to compare them like we did before, except that in this case, we're going to do it slightly differently. So rather than taking my my Sparkle query, which is actually here, let me take it off the cipher very briefly. So this is my Sparkle. I'll bring it back in a second. So why am I doing it in this way? And again, I'm trying to show you tools on how to work with these public data sources. So one of the problems that I found is that the mesh data set offers a number of taxonomies, if you want. And in particular, if we look at diseases, and I expand this tree view, we have a number of subtrees under it. So these are all subtaxonomies that are part of disease, but for some reason, they're not connected to disease directly. So it would be super easy to say, give me all the diseases and that's it. I cannot do that, so I have to enumerate the list of identifiers, which is what I'm doing here, iterating over each one of them and generating, basically running the same Sparkle query for each one of them and returning one tree for each of them. And that's exactly what I'm doing in this query. And because I'm iteratively running it 24 times for these 24 descriptors, I thought I'd rather run it in Cypher from the browser. So all I'm doing is replacing the ID in the query. And that's going to issue 24 requests on the mesh endpoint. And if everything goes well, that should populate my mesh taxonomy of infectious diseases, right? So 24 requests, each one of them returning a bunch of a few thousand of diseases, right? Again, we have viruses, both Wikidata and mesh, the same for diseases, and we could query across them. So we can do something similar to what we did before and show what, for a particular infectious disease, show the two trees, pretty much like we did with the viruses. And we see something similar to what we saw before. So we have the SARS disease here to the right in let's say in Wikidata terms, that links to the equivalent descriptor on the mesh side. And we see that in this case, it's the opposite as it happened before. So the mesh taxonomy is much richer than the Wikidata one. But it's good to have the two of them because that builds a richer knowledge graph. Perfect. Next step. So we have viruses, diseases. The next step is going to be bringing up chemical compounds. I'm going to bring it both from Wikidata and from a mesh. And again, I'm going to give you another tool on keeping control of how portions of data that I bring into my knowledge graph. And I'm going to follow a very similar approach to the one before, except that rather than passing a list of IDs, what I'm going to do is, okay, let's find all the infectious diseases that I've loaded in my database. And for each one of them, let's get its URI, and let's get all the information on chemical compounds that relate to them and pharma products that are associated with them. And essentially, I'm going to run multiple queries the same time, the same query every time, but just replacing the URI with in my Sparkle with the ID of the infectious disease. So I'm going to run it, and it should take a little while. And the reason why it takes a little while, it's going to be easy to understand, is that what we'll leave it running with in Neo4j is that if we look at how many infectious diseases we have in our graph, it's not many, but we have 584. So that means essentially that we're issuing 584 requests to the Wikidata endpoint. And for each one of them, we're retrieving, when present, all the information related to chemical compounds and pharma products for that particular disease. While it runs, we can leave it there. We'll do the same on the mesh side. And in the mesh, we're going to do exactly the same as we did before. We have the list of IDs, and in this case, it's identical. So we look at the chemicals and drugs. Again, we get a list of identifiers of the different subtrees. So for each one of them, and I'm going to be driving this with an enumeration, a list of IDs. I'm going to run the same query, replacing the ID for each one of them. And we can have the two running in parallel. They can take a while, but we can keep moving from there. So hopefully they'll finish. Good. So I think that gives us a reasonably complete view. So we have viruses, we have diseases, we have now we have chemical compounds and pharma products. So we see that the mesh side of the query has finished, and each one of them returning a few thousand triples, each of them. So we can now query across all of them. We'll just bring probably the third element, which is the disease ontology. Just one final step before I run. I'm going to kick it off again like I did with the others so that it gets started and I can explain what we're doing. So the ontology, we're importing it in a slightly different form. So here we don't need to run Sparkle because we're getting the whole ontology and bringing it into the graph. So for that, all I have to pass is the URL of where the document, the ontology, is hosted, and the serialization format. In this case, it's using the XML version. So I'm literally importing all the triples in the ontology, not all of them, because by the ontology import selects the ones that are relevant, but I'm doing some additional transformation afterwards, and particularly what I'm doing is I'm adding an extra label to indicate, again, provenance. So I tag all the classes that have been imported as disease ontology disease. And finally, I'm adding the cross-references to other sources. And in this particular case, the disease ontology also links to the mesh vocabulary. So that's done. Hopefully it's finished. Yeah, there we go. Maybe this one's finished as well. So the chemical compounds and medical and pharma products has finished also on the Wikidata. And we see that, as expected, many of them have returned no results. Again, the Wikidata is not a complete data set; is community contributed. So it's perfectly fine that some of them return no triples, but some others do. So we have now a pretty complete graph. Let's start querying it. Let's see what we built, because that's where the fun begins. So one thing that I can do is this idea of taxonomy reconciliation. What do I mean by that? Let's break it in three parts. So I was mentioning that we have loaded diseases from three sources, and they should link together nicely, forming the triangles that you're going to see. Looks like the browser needs a bit of a refresh. But okay, so what do these three nodes, these three elements in the triangle represent? So we have the green one is the one from Wikidata, and we saw that the Wikidata is linked to both the disease ontology and the mesh descriptor, right? And then we also found that the disease ontology has a cross-reference pointed to the mesh descriptor. So when in normal circumstances, this will form a perfect triangle, and that's absolutely fine. Now, in some cases, and let me refresh the browser so that it's faster, we will see that that's not the case, right? And I'm going to write here. We have some missing bits, so some open triangles, right? And if I, oops, no, it looks like, oh, I've refreshed and I've changed the data bit. Let's go back to our CLS. Sorry about that. So if we run the query, we have some open triangles, which is situations. Let's take this one, for example, where we have an infectious disease from Wikidata that links to the mesh ontology, to the disease ontology, that has a cross-reference to the mesh descriptor, but this is missing from Wikidata. And that's, again, perfectly fine. I was mentioning that Wikidata is not complete, so it's probably a normal situation. But what we can do is, hey, we could produce easily a list of the missing triples, the bits that we could, give back to the Wikidata as an idea of, for example, we could say, these are the triples that you're missing. And I can put it in the form of statements. And basically all these incomplete triangles reflect bits of information that we could contribute to the Wikidata. So, and putting it in the form of RDF, that would be the unique identifier of the resource, the predicate P486 that, like we saw, indicated the mesh identifier, and the actual value that we get from cross-referencing the disease ontology. Great. So that was more kind of a data quality type of exercise, but I thought it was an interesting one to cover. What I'm going to show now is probably more interestingly a query that goes across the 3 different sources that we've loaded. This sort of a cross-domain query, and it's a pretty simple one. So we are effectively looking for data about the common flu, and let's say we want to do a search based on the mesh identifier. So this is the unique identifier in mesh for the common flu, right? So if I run this query, I can navigate from the mesh descriptor to the Wikidata description. And then from the Wikidata, we can navigate also to get the different chemicals that are associated with that disease, the viruses that cause it, etc., etc. So if I run this query, that should produce a nice graph view that starts at the mesh identifier. You see that here's the ID that I used in my query. That represents the common cold, that matches this particular Wikidata representation of the same infectious disease, and it links to the viruses that cause it. So we have the coronavirus and the rhinovirus, but we also see that it's linked to a chemical compound, which is the acetaminophen, that's used for this particular disease, and that is actually the active ingredient for a number of pharma products that we have linked to. So that's an interesting query, I think, where we're kind of traversing across the many different sources that we've used. But we can keep expanding here and probably find that these links also to the mesh descriptor. Also, the common cold is probably linked to other chemical compounds that are also used to treat the common cold, and so on and so forth. So we have a pretty nicely connected graph that we could, although I probably leave that for the next session, complete with information from the Microsoft Microsoft Academic, which is the scientific literature that we could link to these elements. So I'll probably stop the demo here and maybe bring back my slides to conclude. I hope you can see the slides back on. Fantastic. So, right. So what next? Of course, we could, like I mentioned, we could keep bringing extra additional sources of data or additional fragments from the existing data sources that we've been using today, and keep enriching the graph incrementally, iteratively. We could start doing more sophisticated analysis. We can run graph algorithms on the data once we have it in Neo4j. We've created a kind of a curated data set in Neo, based purely on RDF data, but we can now start doing a more advanced analysis. And the same with the ontologies that we loaded. We can do things like inferencing. We can do things like validation. It's probably more than I can cover today, but I would refer you to the sorry, I'll come back in a second to the references to the documentation. But yeah, I thought I'll mention a similar example, a similar project, except that it's done for real, where a number of people from academia and from industry have collaborated with some of our colleagues in Neo4j to build this COVID graph. And again, they've collected data from a number of different sources, and they offer it for researchers, for anyone who wants to get this information. So I think that could be a good inspiration. So here's the URL. And like I was saying before, now it's really up to you. I mean, you have all the code that I've used today, but it's your turn. I mean, it really takes no time to download Neo4j and install new semantics. You have the URL there, and you can either reproduce what I've done today or build your own knowledge graph based exclusively on RDF data publicly available on the web right now. Good. I think I'm, if not over, just getting to the time that I was expecting to spend on these sessions. So I'll probably stop here and see if we have any questions.
Oh, hi, Dr. Barrasa. It's Marilee. That was so awesome. Your demo was excellent. Thank you so much. We do have a few questions that have come in, and we don't have much time, but I want to get to a few of these. And for those of you who have asked questions, if we don't get to your question, you can also shoot an email to webinar@neo4j.com, and we'll get you pointed in the right direction. But we'll try to take a few now. So let's get started with that. So here's one. It says, Sparkle is a requirement to really be able to use the public RDF data sources. Are there alternatives?
Right. Yeah, that's a good one. And it's true that today's session was a bit Sparkle heavy in a way, because we did run a bunch of Sparkle queries that I'm making available in the repository, like I linked before. Well, the answer is yes and no. I mean, you can, like I said before, I mean, maybe you want to just get a full dump of the wiki data, for example, or from the mesh vocabulary, and import it completely into Neo4j. That's absolutely fine. You don't need to write a single line of Sparkle. You just say, here's where the RDF lives, suck it into Neo4j. That's perfectly fine. I would say we could establish the analogy with SQL. I mean, you could import a whole database into a relational database into Neo4j, or you can be, and here's the answer, be more granular. And that's what Sparkle gives you. You can, if you Sparkle in the case of RDF or SQL in the case of relational, you can be more specific and say, I want these particular records in that table. I want these particular triples in this data set. You can also do transformations like I've done today. So sometimes if you import Wikidata, you might find terminology that you're not particularly comfortable with. All these codes may not be super useful and super usable, I would say, not useful, but more usable when you write your analysis. So it's not strictly a requirement, but I think it gives you a lot of flexibility when you want to be granular and when you want to be specific about what fragments of information from these publicly available ones you want to bring into Neo4j.
Great, thank you. It sounds like there are definitely a lot of options. You can go a number of different ways.
Absolutely, yeah.
Okay, here's another one. It says, in this session, you built a graph exclusively with public RDF data. So this might be a related question. But is it possible to use the RDF data to enrich a previously existing graph?
Yeah, absolutely. And yes, I think I kind of forced it in a way, because I said, well, I'm going to use exclusively data from the public data sources. And you saw how I created the graph from scratch and started from an empty one. But you're totally right. I mean, the normal scenario is you will probably have already a graph in Neo4j that you want to enrich. Maybe you have your set of, let's say, of trial information, study information, if you're in the pharma space. Or maybe you have a database of papers with authors, with topics, and you want to link it to public vocabularies. So yeah, the answer is actually that's probably the more normal scenario. So you will have already a graph and you will bring RDF data to enrich it, and you will want to link it together. You can use the notion of URI if you have them in your graph, or you can write scripts in Cypher to do this linkage. So absolutely, yes, that's the most common scenario.
Oh, great. Yeah, that makes total sense, because most people would have something existing that they would need to leverage. Okay, got it. So it looks like we have time for maybe one more. Can I not, or at least in theory, run federated queries across multiple linked data endpoints and achieve the same or something very similar? Right.
Yeah. Well, that's yeah. Probably this in theory makes a lot of sense. In theory, yes, you can, and it's true. You know, to some extent, some of these Sparkle endpoints can be queried in a sort of a federated way. So you can have a client application that actually retrieves data from multiple different sources and combines the results together. With some technical complexity involved, but you could to some extent. We've seen that sometimes the linkage is not as straightforward as it could be. So we need to apply some transformation, which would complicate this approach significantly. But the scenario that I was trying to describe today was more, let's say it was more of a data science one. So where you're a data scientist and you want to, or you're an expert in a particular topic in life sciences, and you want to create a curated data set in your graph database, in your Neo4j, for you to run, like I said at the end, some more advanced analytics. You want to run your algorithms to find centrality. For example, to derive relevance of certain articles, certain topics, or certain chemical compounds. So you want to do more advanced analytics, and that's probably more heavyweight logic that you want to run locally. And actually, that's just impossible to run in a distributed way. So yeah, to some extent, I would say you can sort of combine data from different sources on the fly, but it's not the kind of thing that you would do in the scenario that I tried to simulate today, which is a more analytics-oriented one. And by bringing it to Neo4j, yeah, you get the advantage of having all that practically out of the box, because we have the graph data science library. I haven't touched on it today either, but we have Bloom for visualization. I've done very basic visualizations today through the browser, but with Bloom you can do much more advanced, visual exploration of your data for additional insights. So I think it's a different scenario. The answer is partially yes, but I guess you get a lot more by bringing it into Neo4j.
Thank you. It sounds like we could do a whole other session on the Bloom alone.
Absolutely, absolutely.
Well, I want to thank you again, Dr. Barrasa. That was so informative. We are about out of time for this session. I want to thank the members of our audience for staying with us. We have our last session of the day. It's coming up. It's going to start here in a few minutes. It's Reveal Hidden Patterns in Healthcare Data, Graph Analytics, and the Opioid Crisis. So that should be a good one as well. Again, thank you again, and we'll see you guys in the next session.
Thank you very much. My pleasure.